then what will it? Which mic will it be? Just the laptop mic or?
Just a laptop mic. So for the people in the room, that should be enough. And for the people online, they'll like the computer will become the audio.
Okay.
Yeah, and you can turn on if you're comfortable. You can turn on video and stuff.
Oh yeah, yeah, absolutely. But probably
Oh, I will-
unblur.
Oh, and one last thing. Can you share your screen on this thing?
Oh yeah, of course.
I'll make you a co-host.
I think I actually can already.
Yeah, sorry, I'll make you a co-host or whatever.
No, I think I don't. You don't even need to. I think.
Okay, yeah. But I'll make you a co-host anyway because
Okay.
so people at least turn on it. No?
Excellent.
Yes.
So we'll send the email to math students, I guess. So yeah. It's in interactive peer group. So it's I'm sort of following working. Send we were asking the email to figure it out, but I guess we'll send it after the talk.
I'm hoping there'll be a few more people.
I know for a fact that like a couple of others, like Jonas did it by a couple of minutes, and Jacob will be joining. I know for a couple.
Shall I share?
Well, that's what I'm trying to figure out. I'm trying to make it because as far as I know, I don't really know any undergrads here. I don't think I know any undergrads here.
You're recording, right?
Yes.
Okay. Perfect.
Click. Yep. I am recording. Yep.
Oh, that's
Like at some point, you can take 1 or 2 pictures. That would be great.
yeah.
Cool. There are people on now.
Yeah.
Yes.
Let's give it.
I
passed.
Yeah.
Yep.
And is it usually a very general audience or? Yeah, also don't worry about this. This is just animations. I handle everything.
Oh yeah. So okay, so Jacob.
But like, is there is it like usually very specialized?
Usually like people who've used IT tools before, like or like usually math audience. Yeah.
Yeah. So that's what I figured. I have
Yeah.
some like general introduction. So I need to go pretty fast.
Yeah, you don't have to start by saying like lead is a
Yeah. Yeah. I have one slide like
no, that's fine. That's fine. Yeah.
because these are it's like 90% of these slides are from a different talk that I gave. But that was to a general mathematical audience. So I start off with what is lean. But then it's
no, say
Yeah.
what is in perfectly fine, but like you don't have it doesn't have to be emphasized.
yeah. No. Don't worry. I'm not gonna do a lean tutorial here. Yeah.
You know,
I'm feeling really cold.
should we try some of the email that the science about?
I think it would be good. I think I'm good. Like that is the vision and yeah, and so we know William.
Someone that is for me doesn't have William is a your science grads to years right into school. Oh, see. Presume people want to come to our things all right? But
Yeah. I would think so. I think that's too.
yeah, I guess I don't know that you know. He's not in this. He's open.
That makes sense. Yeah. Very much was doing not an undergraduate anymore. Yeah,
He's now a master's student.
right. Let's give it a couple minutes.
Yeah, sure, sure.
Professional spirit.
Yes. Yeah.
Do you have a picture?
Not too many.
Can you bring like a live like
It's actually a good idea for next time, but I didn't.
But it lives in 8 dimensions.
Yeah, big eight-dimensional jar, yeah.
Yeah. That would be fun, actually. Carry some. The next time I'm giving a talk, carry a few
Yeah.
like tennis balls or something. Just
But that's two-dimensional, I think.
they're three-dimensional, yeah. But, yeah. So is there really a difference?
Yeah.
There actually is a huge difference, but
So.
we don't need to worry about the difference.
Okay, send a message saying
Yeah.
that it started around 5 past. Is that okay?
Cool. Yeah, sure.
Yeah, actually, a reasonable way of representing the dimensions. It's like, I know that, like, like a tesseract or whatever, you can sort of do that visualization that helps. But I feel like you can't really do that with spheres because they're two-dimensional, so there's really nothing to show. It's like, oh, or six inches just dimensional spheres, so it's sort of the way, probably the best way to do it is to just give the coordinates, say like, look,
Oh, yeah, sure. Well, yes. Yes, but I draw a picture. So
Yeah, I mean, maybe there's some way to do it to like, specs the different areas, the volume ratios or something.
So what you can do is you can do something called the Coxeter projection of root systems. And in this case, the packing is a lattice packing, which is essentially the lattice spanned by a root system. So it's like, so you can just take that root system and you can project that down onto a plane, onto a special plane. And that gives you a very nice visualization of the symmetries of the E8 lattice. So I do actually have a picture of that. I have, which is a much more useful picture than
Yeah.
I don't know. I think it would still be cool to have like tennis balls, but I think it'd still be cool. Like you just toss them around like I can also like kind of juggle, but only 3. So that would be fun.
So do we have juggling in 8 dimensions?
I don't know actually.
It's this. Or it's not.
I can barely juggle 3, so that's yeah, baby steps. Yeah.
All right, we seem to have a good turnout online.
Yeah, actually, there's a lot of people. Yeah.
Shall we get? I know.
Good question.
I don't know that Jonas will be coming in a very short while, so maybe we can get started.
Sure.
Yeah. Okay, I'll do a quick introduction and then.
Yeah.
So we're glad to resume the seminar series for this term. Our first speaker is Siddharth Hariharan. He's now a graduate student at Carnegie Mellon University, as of very recently. And previously he was at Imperial College London. In his own words, he moved recently from the London Mafia to the Pittsburgh Mafia. And he'll soon be telling us about the road to formalizing 8-dimensional sphere packing in Lean, a project that he's been involved with for a couple of months now. Over to you.
Hi, thank you. Thanks for having me. Yeah, it's nice to be back in the UK after a few months in the US. And well, I have many more months to go in the US, but yeah. Okay, so I'm going to be talking about 8-dimensional sphere packing. That should work. Okay, is that? Oh, the arrows are not working. Okay, never mind. Anyway, all right. So talk is divided into 4 parts. I'll first talk about what it means to formalize Fields medal winning mathematics. And why I say this is because 8-dimensional sphere packing was famously solved in 2017, and the result earned Marina Vyazovska a Fields medal in 2022. So this is one of the this is maybe the most recent Fields medal winning work that's been formalized. The closest anyone has come to is maybe Peter Schultz, the liquid tensor stuff. But this would also be the most recent work that's been formalized. So if we do manage to get this over the line, it'll be it'll be a huge milestone for the formalization community. I'll then talk a little bit about the informal aspects of the construction. I'll talk about the mathematics of it. And then I'm going to talk about two things that really make sort of the formal aspects of it quite challenging. So yeah, okay. So what does it mean to formalize any mathematics at all? I'm sure everyone here has some idea, but it really usually means expressing it as computer code, which is checked by a compiler for correctness. There are many languages. I'm sure people here have used more than one. I have actually only used Lean, but whatever. I'm, I've read or skimmed Isabel code as well. So trying to get more multilingual as far as formalization is concerned. So there are a few advantages to standardization, centralization, putting everything in one place, but in a manner that's sort of uniform, where everyone knows exactly what it is. So there's the standard way of stating theorems, the standard way of more than theorems, stating definitions. First review processes for publications. There's a very interesting meeting a few weeks ago in Leiden in the Netherlands, where this was an important topic of discussion about how we can use how we can harness the power of interactive theorem provers to expedite review processes and things, and potentially with an AI angle. Proof discovery as well. There's people in this very room who are working on tactics for proof discovery, who are working on all sorts of proof discovery things, and I'm sure they're much more qualified than I could possibly be to tell you about these things. Yeah, there are many applications. And yeah, here's an example of a proof state from our project, from the sphere packing project. This is an actual state where you have a bunch of hypotheses, and from these hypotheses alone, or these, well, some of these are hypotheses, some of these are data. From these alone, you're supposed to deduce that the real part of f of 0, whatever f is positive. Anyway. Why formalize 8-dimensional sphere packing? Well, 3-dimensional sphere packing was famously formalized many years ago by a guy called Tom Hales, who's a professor at the University of Pittsburgh next door to Carnegie Mellon. He announced that he had many, many motivations for wanting to formalize. So he actually announced this formalization effort while his paper was still under review. So it hadn't even been published yet. And part of the motivation was, of course, to remove residual doubts from the minds of his reviewers, but he also wanted to sort of he had this view of him and people like Vygotsky, many people had this view that formal methods are intrinsic to the growth of mathematics, and this is something he wrote about, and it's really in the spirit of those more complex motivations that we decided to undertake this project. So it aims to, first of all, solidify the credibility of 8-dimensional sphere packing, but more than that, I mean, this is a result that this is a paper that hundreds of thousands of people, maybe hundreds of people, have read worldwide, and sort of, a number of people have understood it, under the Fields Medal. So it's pretty well understood work as far as, well, relatively. But it also led to a lot of very interesting discoveries in the direction of sort of radial Schwarz functions and talking about more sort of global optimality results of sort of lattices in these dimensions. And so there's a lot of interesting work that's come out that's sort of based on the ideas developed in Wiazowska's paper. So this would also help lay the foundations for eventually formalizing those. Well, another thing, I mean, we keep talking about benchmarking as something that people do for AI models, but there's no reason why we can't also use benchmarking as a way to evaluate where humans are, where we are in terms of, and not only humans, but also libraries are, to understand how capable is MATLAB of supporting large-scale formalization efforts such as this one, or other efforts that deal with such recent and such advanced, such important mathematics. And of course, we wanted to expand sort of just library building in general. This is a great project for library building because, well, we'll see that it actually uses a lot of ideas that have not been well developed so far in MATLAB, that have not really been treated to formally. And this is a great opportunity to actually do that and to sort of not only formalize them, but really solidify our understanding of these results on which 8-dimensional sphere packing actually depends. So yes, it would be a monumental breakthrough for the formalization community because it's recent, it's extremely decorated mathematics. So this is well, it's a fun project to get on board. So if you're looking for a project, yeah. So who's working on this? How's it going? Well, we have a website, so you can find a lot of that information there. In March 2024, I actually launched this project with Wiazowska herself. So I was doing an exchange program at EPFL, where she's based, and I'd gone to EPFL with explicit instructions from Kevin Buzzard to knock on a door and make this happen. And Kevin came down to give a talk, and she was at that talk, I was at that talk, and that's how this project kind of got started. So it's a very, kind of, this is an example of how, how important it is to just meet people. So, yeah. So over the course of the summer of 2024, a lot of interesting things happened. So there's a guy called Gareth Marr, currently, I think as of last year, he was doing a master's at Oxford. So he and I were working on formalizing some basic theory, definitions of sphere packings and this sort of thing, because we didn't have any of that in the library. Basic results about sphere packing density and so on. I also worked on formalizing an important dependency, which I will talk about in a bit. I'll talk about the dependency informally, not formally. I don't think we have time for that. But yeah, so I formalized quite a lot of this, and there have been some subsequent PRs after we went open source a few months ago, which have filled in some of the holes, some of the stories in this proof. I think this is now nearly done. Chris Birkbeck, who's currently a lecturer at the University of East Anglia, and Siwoo Lee, who's currently a PhD student at Berkeley, have been working on formalizing facts about modular forms and quasi-modular forms. They began working on this stuff partly for this project, partly out of independent interest, stuff that is applicable, useful for this project, but not necessarily, they weren't necessarily doing it for this project. But yeah, they've been contributing quite a lot as well, and they're two of the maintainers of this project now. And yes, between October and June, I worked on formalizing the construction of the so-called magic function. I'll talk about all these ingredients of the proof, but I worked on this one master's project under supervision of Bhavik Mehta, who has been at Cambridge, who was at Cambridge for many years before coming to Imperial last year to do a postdoc. Birkbeck and Lee continued their work. In June 2025, just a few meters from here at the Isaac Newton Institute, Vysovska herself gave a lecture at Big Proof, where we went public, we went open source. And so people knew that we were working on this project, but they didn't know what the progress actually was. But now the repository is open source. Anyone can contribute to it. Anyone can see our code. So we in fact encourage and really invite contributions to this project. And I'll talk about some of the things we need help with if anyone here is interested here or online. Okay, so well, what was this magic function that I talked about? Well, before that, what is a sphere packing problem? Well, it's pretty self-explanatory, really, but I've stated it for completeness. And what Vysovska showed was that in dimension 8, the densest arrangement of spheres, whatever density means, corresponds to spheres centered at points on the E8 root lattice. So this is a very special lattice in R8, which has a lot of symmetry properties. And she was able to exploit these symmetries to actually show, using the theory of modular forms, that E8 packing was optimal in dimension 8. So we can actually project this onto a special plane. And this gives this beautiful picture. And well, what this is really is, so the E8 root system, a root system consists of a bunch of vectors. The E8 root system is, a whole bunch of vectors in R8, and you take the Z span of that, and that gives you the E8 lattice. Root systems also contain, so what you can do is, using the theory of coxeter groups, you can show that there is a special plane on which you can, essentially none of the vectors lie on that plane, and you can just project all of them onto that plane, and that tells you something about the root systems, tells you something about these vectors and about their Z span. So in this particular projection, the nodes correspond to the vectors themselves that belong to this root system, and the edges connect nearest neighbors. So nearest neighbors in Rn. So it's like, so the fact that this graph is so connected tells you that the vectors are actually super close to each other in R8. And that gives some intuition as to why E8 is optimal in terms of 8-dimensional sphere packings. But somehow knowing this is kind of, having this intuition is not nearly enough. Because you need to show that it can't be improved, right? That's really the hard part. Showing that it's a good sphere packing is, well, whatever you mean by good, is not that hard, but showing that it's optimal is very hard. So this was long suspected for these reasons, right? And there was a method conceived in 2003, which said that if you have a certain type of function from Rn to R, so more generally than just 8 dimensions, right? Then you can actually bound the densities of all sphere packings in Rn by a certain quantity, which is in terms of this function. So you essentially get a family of bounds indexed by these functions with specific properties. And then the game becomes, is there a function satisfying these properties such that the bound indexed by it is the density of some known packing? And constructing such functions, it turns out, is extremely difficult. And Bezoska's breakthrough was using modular forms to construct such a function. Let's talk about how you can turn this geometric problem into an analysis problem, right? This is exactly what Kohn and Elkies did, which is why you don't, I mean, the fact that you can't really visualize 8-dimensional spheres in a nice way, I mean, that's not really a problem because of precisely this. So in 2003, they showed that if you have some function f from Rd to R, it's not identically zero and that satisfies these two properties. So essentially, you have you have a non-negativity, non-positivity condition on f and a non-negativity condition on the Fourier transform. Yeah, what this tells you is that you can then bound above all sphere patterns in Rn by, that should be a D, I guess, by this. And if f satisfies all of these and the upper bound is optimal, then we say that f is a magic function in Rd. And we've only managed to find magic functions in dimensions 8 and 24. And it is suspected that you can also find a magic function in dimension 2, although why would you? Because there are much easier ways to solve the problem. But I mean, it still turns out to be an interesting question to ask. But yes, and in particular, it's believed that they don't exist anywhere else, by the way, only in dimensions 2, 8, and 24, which is bizarre. And I think you can do something trivial in dimension 1 as well. But yeah. It's a good question. I think the motivation for trying is just not, I mean, you already know what packing is optimal in dimension 2. So doing this for the purpose of finding optimal sphere packings is kind of, but I think, yeah, I'm not too sure. I think the reason why there is interest in finding one in dimension 2, maybe I should mention that first, is because I alluded earlier on to certain universal optimality results in dimensions 8 and 24, which I really don't know much about. But the point is they envision something similar in dimension 2, which I think, yeah, and knowing something about how or whether you can construct such functions in dimension 2 also says something about these optimality results. So that's why that's interesting. So yeah, a word on Schwarz functions. So these are smooth and rapidly decaying functions. More precisely, every derivative, first of all, has to exist. And secondly, it has to be sort of, it has to decay faster than any inverse power of x or inverse power of the norm of x. So this is precisely the Mathlib definition specialized to the cases of Rd and R. More generally, it can be sort of any R vector space or something, any normed R vector space. And so this is called a Schwarz space, and in fact, Schwarz functions form an R vector space. Moreover, the Fourier transform is a linear isomorphism of this space. So this is an operator which takes Schwarz functions. So first of all, the Fourier transform for Schwarz function is Schwarz, and moreover, the Fourier transform acts linearly. Yeah, composition with any function satisfying some growth conditions. I'll come back to this third point at some point in the talk. But the point is, you also have a way of constructing Schwarz functions from higher dimensions from Schwarz functions in lower dimensions. And so you can kind of, you can work with, for example, what you actually do is in this proof, you work with R to R Schwarz functions and you construct R8 to R Schwarz functions out of those Schwarz functions. And I'll talk about that. But there are some things that this Kohn-Elkies result actually depends on. So first, it depends on, in the proof, at some point, I said that the densities of all sphere packings are bounded about by this. Is enough to show that the densities of periodic sphere packings, periodic in the sense of being periodic with respect to some lattice. So you have a lattice, the lattice will act by translation on Rn, and sort of being periodic is being invariant under that additive action. It is enough to consider periodic sphere packings. And this is something that we don't really have, but Yale has been working on this. The second thing that we don't have is the Poisson summation formula. So what this says is that if lambda is some lattice and f is some function, then you have a relationship, you can sum. So this is like a periodicization of F, right? You're making F periodic with respect to this lattice. And then what you can do is you can just sum over the dual lattice and you get this equality here. And this turns out to be a very important part of this proof, because this is what really introduces this F hat term over there, F hat being the Fourier transform of F. So, so this is also something that we don't have, but we are working on proving this in our end. So currently we only have a one-dimensional version of this, where d is 1 and lambda is the integers. That's all we have in MATLAB. But Aaron Lin, myself, James Cummings, and a couple of other people at CMU are working on this. We've been doing a weekly packathon where we pack spheres. So starting with this. So yeah, maybe we should get some tennis balls for the packathon. Yeah. So, but nonetheless, this is a PR on my repository. So if you would like to look at what we're doing and contribute, that would be awesome. Yeah, so what does Cone-Alkes tell us? Cone-Alkes tells us a number of things. So first of all, it tells us that we can restrict our attention to radial Schwarz function. So we're looking for a function, right? To recap where we are in the problem, we need to find an optimal function from RA to R. So we can focus our search to radial Schwarz functions. And the reason why we can focus on radial Schwarz functions is because so first of all, there was this thing I briefly alluded to, which I'll talk about in more detail, but it was this thing about building higher dimensional Schwarz functions from lower dimensional Schwarz functions. And because we have this way of doing that, we can just consider R to R Schwarz functions. And moreover, the reason why, well, there's another really important thing, right? Which is that before I talk about that, if you just look at these conditions here, we're talking about the norm being greater than 1. And we're talking about, so in condition 2, right? And in condition 3, there's no condition on the norm. So the point is the Cone-Alkes conditions don't actually they only really depend on the norm of X. So, the conditions themselves they don't require X to have any particular properties. It just requires the norm to be greater than or equal to 1, something, like you only want the second condition to hold that the norm is greater than or equal to 1. So it really doesn't matter. F can be a radial function as well. And then you can state equivalent conditions in terms of like that radial bit. And moreover, so if F is a radial function, then it turns out that you can uniquely express F as a sum of a +1 and a -1 eigenfunction. So you can write F plus and F minus in this manner, and then the Fourier transform of F turns out to be Fourier transform of F plus turns out to be F plus. Fourier transform of F minus turns out to be F minus, and this turns out to be minus F minus. But it turns out the reason for that is that the double Fourier transform is the identity when the function is radial and Schwarz. So yeah. So this is something that Cone-Alkes essentially you can deduce already that this function needs to have a whole bunch of properties, right? You can say, okay, if I restrict my attention to radial Schwarz functions, I get all of the structure, and I can use the structure to try and find the right function. So that's the point of this. It also tells us that you can find double zeros at lattice points. So if you view this as a radial function, all of a sudden, you're essentially just talking about an R to R function, and you can talk about what happens at points where the radial bit is the length of an element in your lattice. And it turns out that when it's the length of an element in your lattice, not only should the function be 0, but it should be it turns out that for most of them, it should be a double 0. So the function, if you view the radial part, it should look something like this, and then it'll just be fading rapidly. And it turns out you can show this by looking at the proof of Cone-Alkes, which I'm not actually going to show you. So you just have to trust me. But the point is that, so once you go beyond 1, right? So 1 will be somewhere on this line, right? And once you go beyond 1, you have to be negative by the third condition, and you're smooth, and you can sort of put all the details together. You can see you have to be that has to happen. So this also further informs the search. So essentially, what we need is Fourier eigenfunctions with double zeros at lattice points. So you can put those eigenfunctions together, and then you can So as long as you find the right eigenfunctions, you found the right function. Okay, so we've broken down the problem from being a problem about finding Schwarz functions to being a problem about finding radial Schwarz Fourier eigenfunctions. And then we can use the radial Schwarz Fourier eigenfunctions as long as they have the right properties, as long as they satisfy the right density properties, right? You can put them back together and you get a function that's optimal. Any questions so far? Okay. So what are the eigenfunctions? I'm just going to tell you what they are. But you actually don't need to remember what they are, because it turns out that you can work, well, you can work just as well by looking at pictures. So I'm just going to show you a bunch of pictures. I'm going to show you some definitions, and then I'm going to ask you to forget the definitions and just look at the pictures. So, so this is the +1 eigenfunction. It's a sum of 4 integrals. And I'm not going to tell you what phi naught is. And then B is a sum of 4 more integrals. Except instead of phi naught, you have something called psi s. And I'm not going to tell you what psi s is either. What I am going to tell you is you don't need to remember this. All you need to know is that your integrals are essentially along these 4 contours. And that will essentially give you all that you need to know to be able to follow the stock. Of course, you need to know what the functions are to understand the proof, but this is more about explaining what the challenges are in the formalization. And for those purposes, so if you pay attention, you have the first integral goes from -1 to I, and that looks like integrating from here to here. The second integral goes from 1 to I, that looks like going from here to here. The third integral goes from 0 to I, but there's a negative sign, right? So, at least we look at A, right? So I'm going to do everything in terms of A, and then B will be similar. You look at A, there's a -2 in front of that. So that looks like you're going from I to 0. And then the fourth one is going from I to I infinity. So if you just remember this picture, I'll keep, so this picture will keep coming back to this. And this is all you really need to know in order to understand whatever I'm going to tell you. And then for B, things are similar, not quite the same, but they're similar. Okay, so then you define g of x and f of x in this way. There is a way to get these constants, but the point is that this is now a linear combination of these functions. And then the Fourier transform of A is A, the Fourier transform of B is -B. You can put this together and you can see that it is possible with not some, but a lot of difficulty to show that these are optimal. That G and, well, actually F is optimal. Okay, so what are phi naught and psi s? I said I wasn't going to tell you what they are. I'm going to tell you what they're made of. So they're made of modular forms. So modular forms are holomorphic functions from the upper half plane, which we denote that way in line with Matzliff notation, to C. And these satisfy certain invariance properties under Möbius change of variables. So the point is that SL2Z acts on the upper half plane by Möbius transformations. You can take a matrix A, B, C, D, and then that corresponds to a map. Z goes to AZ plus B, CZ plus D, AZ plus B over CZ plus D, and this is a, this is an action. So what you want is for modular forms to be somewhat invariant under these actions. So if you have something that's weight 4 and level 1, then what that means is that you have this, I guess this is a pointer, right? No. Okay, yeah, I'll use the stick. I can also just point. It's fine. Yeah. So you see -4 here, right? So that's what I mean when I say it is weight 4. So the point is that this is not quite an invariance property. This is like, you have this correction factor, right? It's not just, so it's not just like alpha, it's not just alpha of z is equal to that. It's alpha of z equals to something to the -4 times that. So this is not quite invariant under this Möbius transformation, but it's close. So that degree of closeness is what the weight is. And level 1 essentially means that you're dealing with all elements in SL2Z. So it doesn't matter what A, B, C, and D are, as long as sort of this matrix has determinant 1 and is consistent and is composed of integers. So something that's like level 2 would also involve congruence mod 2 condition. And level K in general involves like congruence mod K conditions. And the weight is this thing. So yeah. So the definitions of the integrands are in terms of phi naught and psi s, right? And the point is that these phi naught and psi s functions are actually made up of modular forms. They're not modular forms themselves, but they're made up of modular forms. And if you're interested in this stuff, I can tell you what they are later on. So for instance, the fact that they're made up of these things gives them these nice properties. So for example, psi s, this entire thing is equal to this. Okay, and you can do this by exploiting some of these change of variables properties. And you can denote this function. If you denote that function by that, then you can show that psi t satisfies this property. Okay, and the reason why we use t is also because well, t is something that forms a basis of SL2Z, so matrix, and that's anyway. So you see these change of variable properties, right? So actually, it turns out that the key to making this entire proof work, the key to checking that A and B are Fourier eigenfunctions, for example, the key to checking that they are Schwarz, the key to checking that they have these double zero properties and so on, it turns out is that they are invariant, or they have these nice change of variable properties, meaning that when you change variables, you get back something that looks similar to what they are. And so this it turns out is a really important part of the step, a really important part of the argument that B hat is minus B. Okay. Everyone kind of with me? And it's yeah, okay. Yeah, you don't need to know too many of the details. I'm just trying to motivate why modular forms are important. Okay, so now I'm actually going to talk about what's difficult about this formalization, right? I'm going to skim the surface. I mean, as you saw in the timeline, we've been doing this since March 2024, and I think we're only like halfway done. So there's still a lot of work to do. But now that I'm doing a PhD, hopefully it'll be easier. Okay, so contour integration. Well, I drew you a nice suggestive picture, but if you just looked at the definitions of the integrals, I just said something like, I don't know, the integral from -1 to I. I never actually told you what the contour is. Which is, you kind of need to specify those kinds of things. And the thing is, Marina doesn't tell you what they are in her paper either. So it's kind of, you just have to kind of, I mean, the reason why she doesn't say anything and the reason why it doesn't actually matter is because your integrand is holomorphic on the upper half plane. So you can kind of move the integrals around, but you can't do that in Lean. Or it's very difficult to do that in Lean. So we were faced with a conundrum. We were like, okay, which of these, there are three options, right? Which of these should we pick, right? So, yeah. Because it's hard. And I'll explain why it's hard. But I mean, maybe you can do it in Lean. The point is that it hasn't been done yet. That's really the point. Yeah, so this is maybe the most natural looking one, but we didn't go with that one. I tried to do some stuff with this, but it turned out to be slightly impractical. We ended up going with this one, and that's why the picture looked the way it did. And the reason why we ended up going with this one is because we have this theorem in math. What this theorem tells us is that essentially what it tells us is that if you integrate around a box, if you go like that, and you're holomorphic on the inside and continuous on the whole thing, and continuous on the closure, then the integral there is 0. And this is a version of the Cauchy-Gaussat theorem. The Cauchy-Gaussat theorem gives this like simply connected domains and stuff. So it's much more general than this. But we only have it for squares and for circles. So we're integrating over a complete circle, then you can, again, use Cauchy-Gaussat. But that's why we decided not to go with this one, because this is not quite a circle, right? It's a pizza slice. And we don't have it for pizza slices. We actually need it for pizza slices, but we don't have it yet. Yeah. So yeah, that's kind of unfortunate. And actually, we'll see that in the double zeros proof, it turns out to be really important that we should be able to deform these integrals, because it turns out, well, that, that gigantic sum of four integrals that I wrote down a while ago, it turns out that that can also be expressed like this, as just sine squared times like a weighted sine squared thing times one integral. And the reason why this turns out to be very useful, well, intuitively, you can see that this, if you just replace the norm of x with some variable r, then then you can view this as like an R2R function, right? Because this is radial. So what you can do is that what you can show is that that function has double zeros at lattice points. And double zeros was sort of, and then so that gives you an indication that this is of the right form. Yeah, so this turns out to be a very important step in showing that the magic function has all the right properties. So this, if you just look at that integral, looks like that, right? And there's a reason why I've marked those special points there. So the way that you prove that our class one eigenfunction A is equal to that is you then write this as you essentially take sine and you use like some Euler stuff to write it as in terms of the exponential. And then you can split apart that integral. You can write it as a sum of three integrals. And those have contours that look like this. And then what you can do is, so now this is looking more and more like the picture that we had earlier, right? Where we had something that went like that. So really what you want to do is you want to take these long vertical ones, you want to collapse them somehow. And to do that, what you do is you start off with the picture that you had, right? And then you go here. And then the thing that we have in MATLAB tells us that this integral is now 0. So now you can change this integral into that integral and this integral to that integral. And then you just keep doing this. And your integrand, as it turns out, vanishes as mz goes to infinity. So you don't have to worry about these things. So this bit vanishes. And then this is how you essentially show that you go from here to here. And you might notice that, in fact, over here, the arrows go vertically, over here, arrows go the other way around, right? And that's because you get two lots of that plus one lot of that, which you can combine to get one lot of that. Yeah, so this is why we need to be able to deform contours. And if we use circular contours instead, this would have been incredibly awkward. We would have had to go like, you need like a, I don't know, like a, is there a name for this shape? If there is, I don't know the name. So we would need something like that, and that's hard, or that looks hard. So it probably is hard. So that's why we decided to use rectangles instead, and that was Bhavik's insight. Actually, he's a brilliant guy. I'm sure, as I'm sure many of you here will agree. Okay, so the Fourier eigenfunction property now. So this is where we actually need that pizza slice thing. Because it turns out that while boxes solve one of our problems, there are many problems. Yeah, this is a hard proof. So before you take the Fourier transform of a function, right? This was that picture that we start off with. And it turns out that after you take the Fourier transform, well, what you want to end up with is you want to end up with exactly the same thing, right? But the way the Fourier transform acts, so there's a reason why I put these in different colors. It's because the Fourier transform actually just permutes these things. So let's go back here. So what's happening is that we had four integrals in our definition of A. And I also mentioned at some point that the Fourier transform is radial on Schwarz functions. So you can show that each of those integrals is a Schwarz function. And then when you apply the Fourier transform, that just distributes over the sum. And you get a sum of four Fourier transforms. So it's like you just take the Fourier transform of the first one to the second one. So the Fourier transform of the first integral is the second integral. The Fourier transform of the second integral is the first integral. The Fourier transform of the third and the fourth is the same. So the third one becomes the fourth one, and the fourth one becomes the third one. So then this picture becomes what happened? Okay, this picture becomes that picture, which is cool. So before you take the Fourier transform, right? If you just look at this part of it, that's what it looks like, right? And then, well, after you take the Fourier transform, the reason why the contour is now dashed is because what that indicates is that the integrand is different, but the contour is the same. Okay, so when you take the Fourier transform, so somehow these are integrals in terms of some complex variable z, right? But these are also functions of some variable x. So when you take the Fourier transform, you're not taking the Fourier transform in terms of z. You're taking the Fourier transform in terms of this function x, right? And in terms of this variable x, right? So you're not actually doing anything to the contours. It's like you have an integral and then you have another integral. You can use Fubini to swap the integrals, and you can just compute the integral of the inside. And then the integral that went outside is still the same. It's still the same contours. It's like, yeah, you have integral, you have like Fourier integral and then regular integral. And then this becomes regular integral, a Fourier integral. And whatever this is, this simplifies to something. And then the regular integral, the integral that you started off with, the original one, it's still -1 to I. And it's also hard to show that it's actually not that hard. We've nearly shown that this thing is integrable and that the function satisfies the properties you'd want it to satisfy to apply Fubini. But that's kind of a separate problem. But once you apply Fubini, you essentially get the same contour, just a different integral. And well, it turns out that what you want to do in order to get this to look like that is you apply a Mobius transformation. You apply a change of variables to this new integral, right? This yellow bit becomes whatever. And then this is now a new integral. And you apply a change of variables so that the endpoints, so that it starts at 1 and ends at I, because you want to make it look like this. But the problem here is, it's not the same integrand, right? The integrand here is not the same as the Brown integrand, right? But then, remember how I said it's really useful, we can really exploit the fact that our functions behave nicely under changes of variables? Well, we did a change of variables to get from there to here. And then after we apply the facts that we know about the integrand, that come from the theory of modular forms, we can show that actually it's the same as the integrand for the Brown bit. It's the same as the integrand for the second integral. So this is now super nice, right? Because we've shown that just by taking the Fourier transform, we can go from -1 to I to an integral from 1 to I with the same integrand as this. And that is extremely nice. So now we're pretty much done with the proof that, you can do the same thing for the red and the blue as well. And then you can use the fact that the Fourier transform squared is the identity to show the corresponding things. So to show that this doesn't just take the green to the brown, but it also takes the brown to the green, and the you can show that it works both ways. So this is now nice. But in order to make this a square again, we need to do some pizza slice stuff. So we have this. And what we want is this, right? We want to deform this into two rectangular things, because then we can use the existing version of Cauchy-Gonzal to turn this into what we want it to be. So this is like the problematic bit, so it's like, it looks like this, which is really the same as, except it's not quite, because the function is pulling behavior right now. So this is really what we're. So I've been saying pizza slice. Well, that's not really I've never eaten a pizza slice that looks like that. But yeah. And this gives you what you want. Okay, so the Fourier eigenfunction property is, again, a very non-trivial and very difficult property to show. This requires this deformation thing that we just don't have, which is quite unfortunate. It's a good question. It's a very good question. When we stop being as afraid as we are to actually do it. No, we have some ideas. No, jokes apart, we do have some ideas on how we want to do this. So Heather Macbeth had some interesting insights, but I think that approach might work. It might be very useful for a lot of other areas. But for this specific contour, there might be an even easier approach, which would rely on showing the existence of antiderivatives inside of circles. So showing something like, if you can just look at circles over here, not quite all the way here. If you just look at circles here, and then show that you have antiderivatives inside, then you might, which should be possible, right? Because you have like Cauchy's integral formula, these kinds of tools. which you do know inside circles. So you can use those kinds of tools and then the existence of antiderivatives to show that this holds inside of a domain where a function is holomorphic. Then it becomes easier, but you're not quite done because the function, forget about being holomorphic at 1 and -1. It's not even defined at 1 and -1. There are singularities. But I mean, the function is very well behaved here because as you approach these singularities, the integrands actually vanish. So it's fine. But even so, there is some work that needs to be done before. So you need to kind of combine the sort of existence of antiderivative argument with a limiting argument. So there's kind of two steps to the process, and it's not entirely clear how we'll be able to do this. So it's a difficult task, and this is something that we're very, very open to discussing. So we have a Zulip channel, and if you have any ideas, just put a message there and we can talk about it. Okay, so complex computations are complex. So this is a very computationally involved proof, right? And what we did was we did some metaprogramming in the process, like a complete side quest. It was crazy. So computations in Lean are very difficult. And we have tactics that help us. You probably know some of these tactics. And NumNum in particular was of interest to us because it simplifies numerals. Now, these guys are all examples of numerals. But things like pi and I are not numerals. And pi should not be a numeral either. I don't know if you should call I a numeral. You certainly should not call pi a numeral. So the idea that we had is that even if I is not a numeral, a complex number might have, a complex number has components, right? It has a real part and an imaginary part. What if the imaginary and real parts are both themselves numerals? Then maybe there's a way to make this work. And there is. So we said, what we can do is we can extend NumNum to handle expressions where the real and imaginary parts are themselves numerals. For example, if you want to do something like this, 3 plus 4i bar times 3 plus 4i is this, right? Then you can just separate that product into real and imaginary parts, and then you let NumNum handle those real and imaginary. You first write this as 3 minus 4i, and then you write this as a pair 3 comma minus 4, and the other one as a pair 3 comma 4. And then you have like a component-wise formula for multiplication, right? Which is well, one way of defining the complexes really, right? So you can just define it as R2 endowed with this multiplication. So this NumNum can handle the components if you just give it the right formulae. So that's what we did. So previously, this is how. I admittedly this is a bit expanded out because I kind of wanted to emphasize some of the steps involved. I'm sure this can be golfed, but it can't be golfed to one line, or at least it could. No, it can't. So this is kind of cool. And this was developed. So this was so Heather Macbeth ran a metaprogramming seminar last year at Imperial, and Edison was a master's student as well, like me, and Kevin, and a whole bunch of people attended this seminar. And it was at that seminar that this idea was born. So she wrote some skeleton code that Edison and I then filled in as an exercise in metaprogramming. So yeah, so this is currently a PR, and I think I've admittedly been much less active on this PR than Edison has. But yeah. Yes, so NumNum I was a NumNum. So NumNum I was a conf tactic, which implements the same procedure as this. But then Heather was able to extend, like instead of having a separate conf tactic, she just used the same. Well, essentially, we'd written a bunch of functions, right? And she was just able to create a NumNum extension that implemented the same things that did the same thing as the conf tactic. So it also carried around proof assumptions basically instead of just simplifying things.
So how general is this? Like if you replace I with like just pi, or polynomial or whatever, like how general?
It only works for I at the moment.
Oh.
But in principle, it could work for something else. I think the problem with having something like pi is that then you're really not talking about, I has this property that I squared is -1, right? Pi is transcendental over Q, and things in Q can be treated as numerals. So really it's Q that you want to be thinking about, not R. So since like Q adjoin pi is like Q adjoin X, right? So it's essentially you're working over polynomials. And that's kind of, you need to think about polynomials differently because they have infinitely many components.
So does it handle square root too? Because I feel like that's sort of the big question. Does it do that?
It doesn't at the moment, but that's not only realistic, like it's also worth thinking about whether we want it to handle things like pi, whether we want it to handle polynomials, or whether we
Square root two.
yes, we definitely want it to be able to handle square root of 2. We definitely want it to be able to do things over quaternions, for example. These are all things that we have in mind. But we first want to see if we can get this right, and then we can worry about other things. Yeah, but Edison has really been championing this, so I'm just, yeah, huge thank you to Edison and Heather. Yeah, and there's also a lot of computations that involve functions. You know, we saw changes of variables, we saw all of these things. There's also a whole lot of so this metaprogramming approach only really works for numbers, right? Or for numerical, well, I don't want to use the word numerical, but it works for expressions involving numbers, right? It doesn't work for, I mean, it doesn't let you simplify things involving like infinite sums of functions or something. So we do want a better way of doing that. There has been recent progress, and in fact, some metaprogramming for asymptotics, but these are not things that we have used or looked into yet. These are things that we want to look into. But metaprogramming alone does not overcome, or at least not yet, it does not yet overcome all of the challenges that come with working with these kinds of functions. So the biggest challenge we faced is carrying around these kinds of assumptions, right? So summability is absolute convergence of sums. Multipliability is convergence of products in all the arrangements, and sort of a slightly it's weaker to what you would call absolute convergence of sums in complex analysis, but it's it's kind of similar in the way that it's designed. It's designed to reflect similar ideas to convergence of sums. Integrability is, well, it's exactly what you would expect to be, except I took measure theory and I never saw almost everywhere strongly measurable. I just saw measurable, but measurable implies this, and really all the functions we work with are they're actually stronger than just measurable. Most of them are continuous, many are smooth. So yeah. But the biggest challenge is when you're keeping track of these properties, when you have an integral, or when you have a sum, or when you have a product of something that isn't integrable, summable, or multipliable, you don't get an error. You instead get a junk value, right? So then keeping track of these things, I don't know, and I've had mixed opinions about this as a design feature. I've come to actually appreciate it because you can exploit it in many ways, but yeah, and really the theorems are all stated in such a way that this is not a problem, because the theorems, wherever you require a function to be summable, in the assumption of that theorem, there is a summability thing. When you require it to be integral, there is an integrability assumption in the statement of that theorem. The place where you really run into these problems is definitions. And there was an example of this where we had a definition at some point where we had a sum that converged, but not absolutely, meaning that the T sum was actually 0. And that's why we weren't able to prove a whole bunch of things about it. We then went back and fixed it. But this was kind of a really annoying thing for us because there's nothing telling us that the definition is wrong, right? Because in some sense, it's not wrong. It's just the error is somehow in the fact that the definition did not reflect what we wanted it to reflect. There was no mathematical problem with the definition. Or maybe it depends on what you call a mathematical problem, right? So unless one is careful, one may not immediately realize that something is wrong. So to avoid dealing with this in theorems, you can use something like has sum, which is completely explicit. There's also a has product, and there's a has finite integral, these kinds of things. But you don't really want to use this in practice because you need to keep carrying around these assumptions. So instead, what you do is when you're proving theorems, you just use this sort of T sum and T prod and integral notation. And that, because that notation is really what comes with this sort of, if the assumption holds, then it gives you the right value. If it doesn't hold, it gives you a junk value. And yes, the workaround is you use that notation and only prove it when needed. And you can actually exploit that to kind of trim down your proofs to not have to prove summability at every stage or integrability at every stage, only where it's absolutely necessary to do so. Yeah, but in definitions, you still have to be really careful. And that was a challenge that we faced. Schwarzeness across dimensions. I said that I would talk about this earlier, and now I finally am going to talk about it. So we saw there was, or I said multiple times, I don't know if you believe me, but I said multiple times that the reason why it's useful to restrict our search to one-dimensional things is because, well, really, what we get is this, I mean, the radiality assumption gives us a whole lot of things. One of the biggest things it gives us is that the Fourier transform squared is the identity. That's really the biggest thing it gives us, if you ask me. Not to mention, it lets you kind of split your problem into a problem of finding Fourier eigenfunctions. So somehow this radiality assumption is it's a hugely advantageous way of narrowing down the search. And that is just, I mean, it was just the strategy to narrow down the search, right? If such a function, like, I can't speak for Vysotsky, but I imagine that if she hadn't found a function with these assumptions, she might have tried something else. But she did find a function with these assumptions, like under the radiality assumption, right? So it's kind of, you know, it would be a good problem solving strategy in a situation like that. And it did work in this instance. But the reason why it was okay to use this is because we know that there was a way to go from 1 to 1, like R to R Schwarz function to R8 to R Schwarz functions. And essentially, you know that if F is Schwarz and G satisfies some conditions, then F circle G is Schwarz. And this is a MATLAB thing. So this essentially tells you that, so this equation here gives you that the new function you get is this sort of composition. And what this tells you is that, so if you have the growth assumptions were having temperate growth and having this sort of polynomial growth infinity thing, HG upper. And what temperate growth is I don't really want to get into it. It says that G is smooth and also some other stuff. So if F is radial, then a great candidate for this function G to compose with is the norm. Because if you have some function from R to R, what's a great way of getting a function from R8 to R that's radial? Compose this R to R function with the norm. You get a radial function from R8 to R. So that's a great candidate. The problem is, I said that this has temperate growth thing requires a smoothness assumption. The norm is not smooth. You run into problems at 0. But it's like super well behaved everywhere else, right? It's only problematic at 0. So the workaround is you take this, so there's a proof here. I know it's a def, but so there is a proof to show that what you get is indeed Schwarz. And in that proof, you need to kind of modify that proof to accommodate cases where G is not necessarily smooth everywhere, but where sort of whenever G is not smooth, if the derivative of F is 0, in this case, we're talking about at 0, right? Where we have one problematic point. But if you can show something like this, if you can show this generalization, then you'll be done. And then, because right now, everything we've done is in terms of R to R Schwarz functions. And somehow, if you wanted to prove that a function from R8 to R is Schwarz, it's extremely difficult to do so, because what you're then talking about is you have to bound all the derivatives. You're talking about bounding like 8-dimensional Jacobians, which is horrible, right? I mean, I wouldn't even want to do that by hand. Forget about doing it in lean. I would much rather do something like this, prove that you can then construct a Schwarz function. This really involves inspecting this proof and changing things here and there, right? This is something that has not been done yet. So if this is something that you would like to do, please be my guest. We'd be very happy to have someone do this. So yes, so missing dependencies are missing details, right? There's so many things from modular forms and from analysis more broadly that are missing. So in modular forms as well, there's a whole bunch of things. I'm not handling the modular form stuff. That's being handled by Bergbeck and Lee, but they have been telling me about some of the things that they're missing. There are many. So there's a whole lot of things that are missing. And we've seen some of this already. There's Poisson summation, there's Cauchy-Gouza. And we can sometimes work around these, right? By instead of working in full generality, which is what you would do for library building, focus on specific cases. So for Cauchy-Gouza, we were talking about rectangular things. So now instead, what we need to do is this. I think rectangle to circle is probably a better way of talking about this than pizza slice. But we do need to we need that. And that's really the only generality in which we need Cauchy-Gouza. We don't need it for simply connected domains that look weird. We only need it for that. And similarly for Poisson summation, there's a large class of functions for which you can use the Poisson summation formula. And really, the only reason why you need why it works for Schwarz functions is because the Fourier transform for Schwarz function has decay properties because it is itself Schwarz. But if you can you can relax those conditions, but then to do so takes more work. So it's enough for us to prove it for Schwarz functions, and already that's a super powerful thing. because even in the one-dimensional case that we have in MATLAB, that is only for Schwarz functions. So yeah, this is enough. But even these are difficult, and because these depend on things that haven't been formalized. So this is why people like you can help, and people like you online. We really, really need help with this. And if you want an idea of what you need help with, head over to, well, you can head over to our website. You can also talk to me. And the whole point is that formalization projects are modular, right? You don't have to understand the entire proof. You don't even need to understand how all the ingredients fit together. It's just that if you choose to work on one particular part of it, you just need to know how that part works. You don't need to know anything else. And this is the huge advantage, right? So you don't have to have understood everything that I said in this talk. You don't have to have just looking at those pictures, you don't even have to have understood those pictures to understand some of the specific things that you want to contribute to. So visit this link. This is the link to the sphere packing sort of landing page, the project website. If you want to get started, there are also links to the Zulip channel. There are links to Marina's original paper. We do have a blueprint as well. There's links to a whole lot of things. If you just go here, that's like your one-stop shop for everything. And you can always message me on Zulip, or you can email me if you have any questions. Yeah. Some references. Yeah.
Yeah, so like with the sort of proof strategy, we kind of reduced from a dimensional problem to a one-dimensional problem, which makes sense. But there's obviously a strong dependence on A, like because the strategy was 1824, and it's sort of a bit unclear how those weird dependency of N comes from. We speak about like sort of where the dependency comes from, how it's weird, I guess.
That's a very good question. So first of all, I will mention that even in our strategy, there is one place where you aren't working one-dimensionally, which is the Fourier eigenfunction property, because you're taking an n-dimensional Fourier transform, which is fundamentally different from taking a one-dimensional Fourier transform and then composing with it doesn't work that way.
Yeah.
You have a square there which does not commute. So so that is somewhere where we have a dependence on n. But in terms of the specific structure, right? Why 8 and 24 are these special cases? It's because of the definitions of the functions phi naught and psi s. Is because these functions are defined in terms of certain specific modular forms. So phi naught is defined in terms of the Eisenstein series. Is defined in terms of E2, E4, and E6. And E2 is not modular, but it's close enough for our purposes. And psi is defined in terms of the Jacobi theta functions. And it turns out that the reason why dimensions 8 and 24 are nice is because you have these highly symmetric lattices, which means that when you define something in terms of modular forms, it kind of, it still works. In other dimensions, you don't have such lattices like the E8 lattice and the Leach lattice. I don't think they're known yet. I don't want to say they don't exist. I don't know the first thing about dimension 23. But
Okay, yeah.
Yeah.
What's so difficult about the coefficient project for general controls?
it's a good question. I think there are many problems. So first of all, if you had something like, let's start with something that looks very simple, right? Something very innocuous, like a triangle. Okay? So in fact, when I learned complex analysis for the first time, it was like we were first taught how to prove it for triangles, and then how to prove rectangles from here and for anything. I think you can do rectangles and then triangles as well. But so how I would prove this using what we have, would be to do some kind of staircase thing, where I say something like, I then reduce this to that, and I reduce this to that, then. Is that right? Yeah, whatever. So I would do something like this, right? And you can prove then sort of, you can define essentially a sequence of functions, right, in terms of this. And you can prove that the integral, where essentially you've parameterized these contours, you can define a sequence of functions in Fn from like 0, 1 to C or something like this. And you can then show that by using something like dominated convergence and this thing convergence. But how do you define each Fn individually? Like you have to express it as a bunch of different cases or something. And that's already super awkward to put in D. Now, if you wanted to do this in a situation like that, what do you do? Like I don't know what to even do. It's kind of it's it's there's like the fundamental challenge of just understanding what an abstract shape looks like and thinking about if I have some abstract shape, like what do I don't know what you would do in some sense, right? It's a bit awkward to do it. To do it not handmade, I think. I don't know. It's just it's just difficult to
Difficulty is actually not on that complex integration. It's really just showing that any reasonable cube shape can be approximated.
not only by rectangles, but by rectangles of diminishing size.
Simple,
Right?
yeah, you need dimensions. So
Yes. But so something like this is, I think, the challenge. And not only that, but sort of having an explicit way of writing these rectangles down. You want it to be explicit in some sense, right? Because kind of writing down these functions.
So if you get triangles, and then you can kind of those say real love and triangles, like big polygons. Will you approximate like with polygon, say like a fish sort of it's more or something like that.
Going in?
So try and draw a polygon, sort of like an inscribed polygon, make a polygon and one some kind of say that points halfway between each other, sort of like project out.
Oh, to go from here to here.
Yeah.
I see. Yeah, probably.
Yeah. I mean, I guess like you get to the all without.
But this one, but a convex something.
Yeah, before so I guess.
Yeah.
It seems like sort of reasonable.
Yeah, so it's kind of strange. We actually do have it for circles. So maybe you can combine circles with something like this somehow. But again, it's kind of if that's another reason why this would be so useful, right? Because right now we don't have a way of we can't harness what we have for circles, prove stuff about polygons because we don't have anything that looks like straight lines and curves.
Especially if you triangles though, because you can use the triangle to draw.
Yeah, we already have circles.
Yeah, we could get an arc, right, which would give you a robust pizza slice because it's going to work just as well to create a pizza slice from last week than it would for like a whole circle. So it's like a slightly general result. But yeah, you can get super awkward things. But anything circular, you'll be able to.
Yeah.
I think the idea is like one, you do a triangle. Once you have a triangle, you can do any polygon. By composing a triangle.
Yeah.
So you can do any polygon, you can do anything piecewise linear.
Yeah.
You can, if it's like a nice enough shape, you can approximate it with piecewise linear. Circle would be similar to.
Yeah.
And then that's we probably.
Yeah. No, that'd be a very good idea. I think because also if you do manage to do it with triangles, then it means you've already kind of perfected this. You have some idea of how to do this limiting thing.
Well, I would say you do it for triangles and then not just triangles that are. But
Yeah.
And once you've done that, then you don't sort of need to do the argument again.
Agreed.
Same way.
Yeah, absolutely. You have this, and then you have that, and then you have that. Right?
Yes.
This then becomes smaller and smaller and smaller. So I mean that you again have the same. Yeah, that's what I mean. Yeah. So you've done it once, then you also know how to do that as well. So you get that bit for free. Yeah. No, yeah. That would be fine. But again, that's it's not been done yet. So
Well, I guess what I'm talking about, you prove the triangles, then you prove that if a function has to then it doesn't really exist. And then you need to like to change how triangles you just use that.
right. So that's how we want to do this now. So that's another strategy that we want to. So that's actually how we want to do this. Actually, you're right. I don't see why that wouldn't work for more. Yeah, right. Something like that. So there's really two things that you need to show with that shape, right? So one is this, you can use sort of existence of antiderivatives, I guess, to show that if this is contained inside something where you have antiderivatives, then you're fine. There's also this awkward thing that as you get closer to this point here, you're actually approaching a singularity. So you need a limiting argument. That the function isn't even defined over there. So you need sort of, you need to approximate things that look like. Whatever. Then you, this is a terrible question. I'm sorry. Yeah, I think I think you see what I was going for. That's a bad drawing. I'm not good at drawing. Yeah. Yeah, I think that is maybe how we want to do this. Yeah, because doing it this way is awkward, right? That's maybe how we want to do it.
Yeah, if not, it's.
Okay, thank you.